Right then, let's talk about something you probably use every week, but never really think about. The humble Hoover, or as some people insist on calling it, the vacuum cleaner. It's a simple idea really. A machine that sucks up all the dust, the crumbs from your biscuits, the bits of fluff that seem to appear from absolutely nowhere. It's a box on wheels that makes a bit of a racket, but it keeps our homes from descending into a complete and utter mess. We've all got one, tucked away in a cupboard, ready for action when things get a bit grubby. It is, quite simply, a brilliant bit of kit. But have you ever stopped to wonder how it's made? What goes into creating this machine that wages war on dirt? It doesn't just magically appear on a shop shelf. It starts its life as a jumble of raw materials, little pellets of plastic, spools of copper wire. It's a journey of fire, pressure, and incredible precision. A dance of robots and human hands, all working together in a massive factory. Today, we're going on a tour. We're going to pull back the curtain and see exactly how one of these things is born, from a designer's doodle to CAD and prototypes to the finished article. This isn't some high-tech supercar we're building. There's no carbon fibre or V8 engine. But the process is just as fascinating in its own way. It's a story of engineering made for everyone. We will follow the step-by-step build from the very first plan to the final box. Every single thing that gets made, a pencil, a passenger jet, starts life as a plan. And a Hoover is no different. It all begins in a quiet, well-lit room with designers and engineers. These are the designers and the engineers. These are the clever people who sit around and dream up what the machine will look like. They sketch out its shape, deciding if it will be sleek and modern or sturdy and traditional. They argue about where the buttons should go, what colour it should be, and how it should feel in your hand. This is the art of the machine, the part where function meets form. Once the designers have a drawing they're happy with, it's handed over to the engineers. They take the beautiful drawings and use powerful computers to build a virtual three-dimensional model of the Hoover. This digital testing phase is incredibly important. It saves a massive amount of time and money. Imagine building 1,000 Hoovers only to find out there's a critical flaw in the design. It would be a catastrophe. By using computer simulations, the engineers can find and fix problems before the factory even orders the first screw. They can tweak the shape of the fan blades for more power, or adjust the path of the air for less noise. It's a process of constant refinement, making tiny changes until the plan is as close to perfect as it can get. When everyone is finally satisfied with the computer model, a physical prototype is often built. This is the first time the Hoover exists in the real world. It might be 3D printed or carefully crafted by hand. This prototype is then tested relentlessly. It's pushed, pulled, run for hours on end, and used to clean up all sorts of messes. The engineers are looking for any weakness, any rattle, any part that doesn't feel right. Only when the prototype passes every single test does the plan get the green light. The factory is told to fire up the machines. The real work is about to begin. Now that the blueprint is locked in, the factory needs to get all the ingredients together. Making a Hoover is a bit like baking a very complicated cake. The main ingredient by far is plastic. It arrives as tiny little pellets, almost like grains of sand. These pellets will be melted down to form the main body, the wheels, the dustbin, and all the covers. It's a strong, lightweight, and relatively cheap material, which is why it's perfect for the job. You wouldn't want to lug a Hoover made of solid steel around the house. Of course, it's not all plastic. The heart of the machine, the motor, needs metal. lots of it. Great big spools of gleaming copper wire and steel delivered in sheets or bars. Steel is cut and shaped to form the motor's frame and structural parts. Then you have all the smaller bits and bobs, bags of screws, boxes of bearings, rubber for seals and wheels, and the bristles for the brush roll. Managing all these materials is a huge job in itself. A vast warehouse stores everything, organized by computers. A forklift picks up plastic pellets here, a crate of motors there, delivering them just in time to the correct station. It's a highly efficient, carefully choreographed ballet of logistics. Quality is checked from the moment materials arrive. Pellets tested for purity, metal for strength and thickness, even screw threads inspected. If any batch doesn't meet the standard, it's sent straight back. This first step of quality control is vital. It ensures every part will be strong, reliable, and fit for purpose. With all the raw materials in place, the first big manufacturing step can begin: making the plastic parts. Little plastic pellets transformed into the recognizable shapes of the Hoover's body. Injection molding, the process used. The pellets are fed into a giant machine. They are heated until they melt. Molten plastic, thick, gooey, like honey. Immense heat and pressure bring it to a perfect molten state. The molten plastic is injected at extremely high pressure into a mold. The mold is a heavy two-part block of steel precisely carved to shape. Example, the main casing of the Hoover. The hot plastic fills every nook and cranny of the mold's cavity. Water is pumped through channels inside the steel mold to cool it rapidly. As the plastic cools, it hardens, taking the mold's shape, like making an ice cube, only much hotter and faster. After just a few seconds, the mold splits open. A robotic arm removes the newly formed part. A human operator may also remove parts. It's still warm to the touch. Screw holes, vents, clips. The speed is astonishing. One machine can churn out hundreds, even thousands of identical parts every day. The process repeats, melting, injecting, cooling, ejecting, building up stock for assembly. Now we move on to what is arguably the most important component, the motor. This is the powerhouse, spinning a fan at incredible speeds to create suction. It starts with copper wire. A machine winds it tightly around a core, the armature, creating electromagnetic coils. The armature sits inside a sturdy metal casing with powerful magnets fitted around it. Electricity through the coils meets the magnetic field. That's what generates rotation. Tiny ball bearings are pressed into place at either end of the shaft to reduce friction. So it can spin thousands of times a minute, smoothly and reliably. A motor must be perfectly balanced. A fraction of a gram off causes violent vibration. That would make the Hoover noisy and shake it to pieces. Each motor goes on a balancing machine that detects any imbalance, then drills tiny holes or adds minuscule weights to perfect it, like balancing your car's wheels, only smaller. Before the line, motors face rigorous tests. Full speed runs, listening for noise and vibration, power consumption, rotational speed and temperature, all must be in spec. Any that fail are rejected. Only the strongest, quietest, most efficient motors earn the right to be the heart of a new Hoover. Now they're ready for final assembly. This is where the magic really happens, putting it all together. All the parts we've seen, the plastic body, the powerful motor, the metal components, all come together at the assembly line. A long, moving conveyor snakes its way through the factory. At each station, a worker, or sometimes a robot, has a specific job to do. It's a carefully choreographed dance, where each step adds another piece to the puzzle. The empty plastic shell is placed on the belt, starting its journey. At the first stations, core components are installed. A worker takes a fully tested motor and secures it inside the housing, tightening screws to precise specs. Next, the fan goes on the motor shaft, and rubber seals and gaskets create the airtight path for suction. Each person is a specialist. Repetition makes them fast and expert at spotting tiny problems. As it moves down the line, it looks more and more complete. The dustbin or bag holder is clicked into place. Wheels are attached, letting it roll smoothly for the first time. The main handle is secured. Robots excel at heavy lifting and inserting hundreds of screws, but human hands handle delicate tasks, feeding wires through narrow channels, clipping fragile parts. Robotic strength plus human dexterity makes the line so effective. The pace is steady. No frantic rushing, just rhythmic flow. Perfected over 100 years, it's the key to mass production. With the main body and motor assembled, it's time for the finishing touches. One of the most critical steps is wiring. A worker carefully connects all the electronic components. The power cord is attached. The on-off switch is wired up. Fancier models get a small circuit board for power levels or sensor lights. Every wire is color-coded, routed neatly, and clipped so nothing rubs or pinches. This demands immense concentration. Next, the brush roll, the part that does the dirty work. It agitates carpet fibers to loosen deep down dirt and hair. It's fitted into the head and must spin freely. Some brushes have their own motor, others are belt-driven from the main motor. Bearings are checked and properly seated. Without the spinning brush, it would merely skim the surface. Then come the filters, vital for the air you breathe. A Hoover sucks up microscopic dust, pollen, allergens. Filters trap these so they aren't blown back into the room. Many modern Hoovers use HEPA filters, fine, pleated filters that capture almost all tiny particles. A worker carefully slots the filter to ensure a tight seal. Sometimes multiple filters are used. Hose connected and seals checked. Wand and tools prepared. For floors, curtains, stairs, even your car. For the first time, the Hoover is a complete machine. But its journey isn't over yet. Before a single Hoover leaves the factory, it must face the Grand Inquisition, tests to guarantee it is safe, powerful, built to last. First, electrical safety. Each machine is plugged into a special rig that sends high voltage through it to find wiring faults. No metal parts can ever become live. A green light means safe. Red sends it straight to repair. Performance is measured scientifically: suction power, airflow, water lift. Readings must be within a tight range. It's run on different flooring, deep pile carpets and smooth hardwood. Inspectors pull random units for torture tests. Hundreds of hours run, rolling over step edges, bumping into walls, and noise level checks. At the end of the line, every Hoover is switched on by a human inspector. Motor sound, buttons, lights, and finish are checked. It's the final seal of approval. It has proven it's metal. Packaging is more important than it looks. The box's main job is to protect the machine on its journey. The Hoover is placed in a custom box with supports, hose, wand, and tools tucked in. The instruction manual is added. Boxes are sealed and labelled with model number, serial, and a barcode to track it worldwide. Boxes stack onto pallets, whisked into the enormous warehouse. Lorries load pallets for regional centres, then out to thousands of destinations. Some go to retail showrooms, others to online warehouses, waiting for you to click buy. A complex logistics network gets it from factory floor to your front door efficiently. And so, the journey is complete. The next time you pull your Hoover out to clean up a mess, think about the incredible journey it has taken.